Now let's try another example. This is an example of a back titration. So let's see how a back titration is different from a normal titration. Now with a back titration, for whatever reason, the substance that you're trying to find out cannot be dissolved in water. So it has pretty limited solubility. So instead, you either dissolve it in excess acid or in excess base. And then you titrate the excess. So let's look at this example. We have 1.5 grams of chalk, and you can't find the moles of chalk because it's not a pure substance. And it's dissolved in 10 ml of 4 molar hydrochloric acid. Now this would be in excess. So there's too much hydrochloric. So we're expecting there to be hydrochloric acid left over. It is then made up to 100 ml. So our diagram so far looks like this. Here's our 1.5 grams of chalk. We've dissolved it in 10 ml, 4 molar acid, and this is in excess. And then it's made up to 100 ml in total. We then take a 25 ml sample. So we pipette 25 ml, and this is our excess acid. And it is titrated against sodium hydroxide, which has a concentration of 0.2 molar. And we use 18.75 ml. Now with a back titration, there will be two chemical reactions. Our first chemical reaction, calcium carbonate plus 2 hydrogen ions goes to calcium ions plus water plus CO2. Now, this chemical reaction is corresponding to what happens over here. Our second chemical reaction is our standard acid-base reaction. Hydrogen ions plus hydroxide ions gives water. And that's what's going on over here. So, let's get started. Part A, the number of moles of sodium hydroxide used. So we're talking about the number of moles of sodium hydroxide used in the titration, which you can see here. You've got a concentration and a volume. So the number of moles of sodium hydroxide is equal to CV, which is 0.2 times 0.01875, which comes out to 3.75 by 10 to the negative 3 moles. Part B, the number of moles of excess hydrochloric acid in 25 ml. Well, using our balanced chemical equation, you can see that 1 mole of hydrogen ions reacts with 1 mole of hydroxide ions. So the number of moles of hydrogen ions or hydrochloric will be the same. Now I must write this down because there are often marks given for it. Part C. It says the number of moles of hydrogen ions in excess in the 100 ml. So we know there were 3.75 by 10 to the negative 3 moles in 25 ml. So we want to know the number of moles in 100 ml. So this is a simple ratio. So the number of moles of HCl in 100 ml will equal 3.75 by 10 to the negative 3 times 100 divided by 25. Now you would expect there to be more because it's a greater volume. So this is why the 100 is on top, because it's a much bigger volume. So then this will come out to 0.015 moles in excess. Now, Part D. Part D says the number of moles of hydrochloric acid originally present. So for Part D, the number of moles of HCl at the start is equal to CV, which is equal to 4 times 0.01, which is 0.04 moles. Now, part E. The number of moles of HCl used to dissolve the calcium carbonate. So, the number of moles of hydrogen ions used in reaction 1 will be equal to the number of moles of hydrogen ions from the start minus the number of moles of hydrogen ions in excess. So the number of moles at the start was 0.04. The excess we have calculated from our titration, so it is 0.015. And this comes out to 0.025 moles. So now we're up to part F. It says the mass of calcium carbonate present in the chalk sample. So using reaction 1, we've got the number of moles of hydrogen ions that reacted, so we can find the number of moles of calcium carbonate. So the number of moles of calcium carbonate, using our balanced chemical equation, unknown over known, times the number of moles of hydrogen ions or hydrochloric, is equal to 1 over 2 times 0.025, which equals 0.0125 moles. Now we have to find the mass. The mass of calcium carbonate is equal to number of moles times formula mass, which is 0.0125. Go to the periodic table and work out the formula mass is 100.09. And this comes out to 1.25 grams to 3 significant figures. Part G is find the purity. Now remember, the percentage purity is equal to the mass of the pure over the mass of the impure times 100. So the mass of the pure was 1.25 divided by 1.5 times 100. And it comes out to 83.4%. Remember, our answer must be given to 3 significant figures.